Hello, math magicians. On this great day, we're going to be graphing and analyzing the function that's tangent as theta gets mapped to the tangent of theta. We're also going to discuss something called periodicity of the three basic trig functions. But by way of introduction, let's take a gander at what periodicity is. Here is a YouTube video on the Bay of Fundy tides. Something to notice here that as we are watching the video is that we already see the corrosion of the rocks right here. So here's the tide coming in. Whoa, everyone's running away. Because it's actually quite dangerous. If you get stuck down here, you're actually stuck. Notice how much it comes up. Boats coming through, kayaks, and then coming back down. And it's going to repeat the cycle very, very regularly. So out it goes, and then it's going to come up. So this is one of the highest tides, if not the highest tide change in the world. Well, that's what periodicity is. It's about things that are changing regularly and then repeat themselves. So we've already looked at sine and cosine and how they flow, and just as a reminder, just flows something like this. We called that curve sinusoidal. Well, today we're going to look at something slightly different, and we are going to use the unit circle that has tangents on it in order to find out these results here. So if this is theta being 0, and my tangent is 0, so tangent is 0 here, and at 30 degrees, it is radical 3 over 3, etc., and there's my decimal equivalent. Well, notice that the repetition occurs. Notice it's symmetrical here. So at 120, it's going to be the same as 60. So this one is going to be radical 3, hence the approximation is the same. Next, we're going to be at 1s, and radical 3 over 3, except what's my change? We are now in the negatives here. And this last one here is 0.577, but let's keep it in the negatives there. Now what do we notice? As we look at the next one, we notice that the tangent of 210 is the same as the tangent of 30, positives again. Once we get here to this undefined point, we end up getting tangent going negative again. So, in other words, what happens here, beginning 30 and 210, it repeats. Whatever happens here happens exactly here as well. So we can just transfer that stuff down. And there I've done it, just done a direct transfer because it repeats. So now let's walk through and see what the function here looks like. So the first ones are done for us right here. So here's this, and then here is this. So undefined is going to be at 90 degrees. We can't plot a point at all. But we notice that there's this quick jump. Now, what happens after? So, like we said, we know that 210 is the same as 30 degrees. And 0 is the same as 180. So 210 is right here. So it's going to match up right there. Next, just shifting over just a little bit to put it matching there, and shifting over just a little bit to match with that other one right there. What do we actually notice? We notice that at 90, there is no point, and at 270, there is no point. Plot there. So, and continuing on, here we have repetition that occurs here, here, and here. So notice as we draw the curve, that is going to asymptote. It's never going to touch, and at 360 is 0 right there. So we notice here that we get sort of like claw marks on this thing here. And when you check with your graphing calculator, you'll end up with graphs that go like this. So to me, it looks a little bit like claw marks, because as the claws go down, they never intersect with each other, but they do curve. So it's not parallel lines, but it's kind of like parallel curves here. So that's what tangent looks like. So the question is, how can we draw this quickly? Since we already know how to quickly draw the sine function and the cosine function. So let's walk through here. First off, what happens is that there is an occurrence of asymptotes that happen at 90 degrees and then 270 degrees, etc. If we're looking in terms of radians, it's on the halves. On the halves, we get asymptotes. On the halves, like so. So if you first draw your vertical lines at the asymptotes, like so, that make the asymptotes, then we have boundaries for my lines. Next, we have zeros. The zeros happen on every pi, pretty much, which is every 180 degrees. So 0 here, pi, 2 pi, negative pi, negative 2 pi. Another thing to consider is that when we do graph it, we notice that actually most of the changes are going to happen between -1 and 1. So notice that my scale on this particular graph goes all the way up to 10. So I'm not going to do a smooth, gentle curve like this. What's actually going to happen is that most of the curve happens right here. So for this particular graph, because the scale has been is going to squash the curve, it's going to look more extreme. So what's it look like? Well, we're going to start high, come down sort of gently, and then right when we get into the 1 area, we're going to shoot over. So gentle, 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 then we get to the 1 area, push, shoot over like so. And to complete this, just shoots over like so. And of course we have our asymptotes that occur and shoot over like so. And it's going to look sort of like claw marks, like so. So this is just a quick sketch to see how the tangent function looks. Now your job is real quick to sketch in the planes below first the sine function, so y equals sine of x, and then down here y equals the cosine of x, using your shortcuts from previously. So now what we're going to chat about is periodicity and trigonometric functions. So many phenomena in real life, in actual real life, are what's called periodic, okay? That means they repeat the same exact thing over and over and over again. Moon phases are one of them. Tides is another.
Parts of the
Calendars, seasons repeat themselves, etc. So all of this has to do with periodicity. So here is the mathematical idea of periodicity theorem. For any real number x and any integer n, the sine of x is equal to itself when shifted. Remember what this means. This means a shift. And again, it doesn't actually matter which direction we shift, left or right. It depends on your value of n, if n is positive or negative. So the shift happens in both directions, and it means multiples of 2 pi, or multiples of 360. Okay? So every 2 pi, it maps back onto itself. So let's see what that looks like. So let's see here. Let's take a gander at our function here. And the function is sine. So here's sine. And what I'm going to do with sine is that I'm going to shift it. And notice the shift here, that as I shift it to the left, it now maps to itself right there. Now it's back on itself. And again, notice 6.28, that's 2 pi or 360 degrees. So I can keep going up, shifting to the left, 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 boom, back onto itself at 12.566, etc. And it doesn't matter if I'm going left or right. Maps onto itself here, maps onto itself there, maps onto itself there. So that does work with cosine, the same shifting over here, but notice the slight difference here. For tangent, it's not the same. For tangent, it's not the same. It's in 180 degree increments or pi radian increments, okay? But the idea is still the same. So the periodicity theorem can be summarized as a function maps to itself when shifted.
a particular amount. I mean, it could be shifted left, right, 1, 2, 3, pi, whatever. So some shifting amount happens. We call it the period. The period is the positive number. Of course, it can be negative in the sense of we can shift left or right. But in this case, we're just calling it pi, or we're just calling it 2 pi. So we're talking about it as a positive number, even if you can go left or right. So such that when you do the shift, it maps to itself. The shift maps to itself. And the periods of the trigonometric function, the trigonometric functions are, so for sine, the periods are 2 pi. And cosine, the periods are 2 pi. And for tangent, the periods are just pi. Sweet. To unpack a little bit more, moon phases, new moon to new moon is 29.5 days. So roughly 28 days, which is why it's close to a month. Hence the name month, moon. You can see it kind of in there. Like I said yesterday, the tides that we dealt with at the Bay of Fundy, which is the highest tidal change, that happens every 12 hours. A little over 12 hours, it goes from the lowest tide to the highest tide. And it's something like 48 feet change, a 5-story change in tide height. So obviously a calendar, every 12 months, we're back to January. Seasons, again, somewhere about 12 months, we're also back there. All right, so the periodicity, we're going to use the periodicity theorem to find the cosine of 2,670. Now, of course, this one's not very crazy because all we have to do is essentially divide and use the remainder, okay? So we have to divide 270 by the period. And what's the period for the cosine is 360. So we get 7.416, etc. Now, when we're doing this, because it wraps around itself 7 times, it completes the cycle 7 times, we can ignore the 7 and just focus on the decimal part of the cosine. So when we take the decimal and multiply by 360, this will give us how many degrees left over. Now, this is equivalent to the cosine of 150 degrees. It just goes around 7 times first.
Wait.
Yeah, if there was no decimal, then that means it would just be the same because it's made the
Now for cosine of 50, we actually know that exactly using our unit circle, 150. And then negative radical 3 over 2 is what we get for our, and we can use the unit circle to do that. So this is an exact. Is it possible to plug this right here into my calculator? Actually, yes, your calculator can manage this. So notice specifically, this says, please use the periodicity theorem in order to find it. So you have to show the modulo work here to find the remainder, and then use that with the unit circle. So essentially, not only are we finding cosine, we're finding exact value. So for this type of problem, we want to see the work and find exact value as opposed to just plugging it into your calculator. So go ahead and attack example numero dos using the periodicity theorem. All right, and coincidentally, we get the same answer here. And remember that sine is the y value on the unit circle there. All right, the last thing we're going to look at on periodicity is other situations besides sine, cosine, and tangent that also have a period. So in this case, the graph below shows normal human blood pressure. So here's time, 11.6 seconds, 11.8 seconds, and 12 seconds. And here's the blood pressure. The pressure increases, decreases, increases. But this is where you go, thump, 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 thump. So that's your heart rate or your heart pumping, creating more pressure. And of course, as the pressure releases, your blood flows, etc. So blood pressure is called systolic when the heart is contracting. So here it's contracting, it's building up the pressure. Systolic is way up here, the pressure is high. And then it expands to release it, called diastolic, when the heart is expanding. The changes from one to another, create the pulse. And for this function, we're going to determine each. What's the max and min values? So we're just reading the function, reading the graph. We're going to find out the range for this particular graph, and then the period for each time. Yeah, just the period. So here we go. What's the max and min? Well, it looks like max is here, right? Or any of those. Well, or it even looks like if we go at this, some of these are slight variations. So if you chose this one over here, that's probably actually even closer. So A, your max, is approximately, it's slightly under 130. So if you said 128, etc., or 127, that would be sufficient. My min is somewhere down here, and I'm not choosing the label because it's labeled. I'm choosing it because it looks like it's the lowest there. So if you had to guess on that one, I would say the min is approximately 87, 88, something like that. All right, next, the range. The range is just talking about how high and low the range goes. The range is the y value, so the high and the low, pretty much. So it is approximately 128 minus 88. Approximately 40. Our unit looks like it's millimeters of mercury, which don't know exactly what that is, but that's the unit we're using. And lastly, what's the period? The period says, when does it begin to repeat itself? So the period, and we can choose any low point to low point or high point to high point. It actually doesn't matter where we go. You just have to get from until it repeats itself, right? So the period is going to be from here to here. So that's going to be my period. Now, if I were to look down here at what that represents, that's going to be somewhere here to somewhere here. So that's a little bit harder to estimate here because if this is 11.8, that's 11.9. So this is like approximately 11.96-ish,
Yeah.
maybe. And then this one here is 12.1-ish, so 12.15 is here, so this is like 12.13. So I'm just estimating. So after I find the distance there, I subtract it, I get approximately 0.17 seconds.
Is this person like freaking out?
So every 0.2 seconds, you get the whole beat occurs. Now it's your turn. Please attack, kill, destroy. Example 4. When you are finished with that, update your summary and your questions, and then begin working on the assignment.